right, did you guys have a chance to read the subroutine stuff? No? Kind of, a little bit? Okay. Well, we'll talk about more about subroutines today, and depending on how far we can go today, we may be able to get into local variables today, which is a separate concept. So now, are there any questions about the homework assignment that is due on Thursday? What homework assignment?
It's not Thursday yet.
Yeah, it's due on Thursday, so I don't think there should be a whole lot of issues, but if you have any question about that, it's time to ask that question, ask those questions. As I said, there are multiple notes for this particular topic. The updated one is actually the one that is probably easier to understand. The other ones are still good, they're still consistent with the last one. But if you have to focus on one particular link, I would focus on this one, because this is the last or the most up-to-date version of my notes regarding subroutines and how to trace subroutines. The other ones may explain the concept better, but this one definitely shows how to trace subroutines better. So there is that. The projector is projecting, I think, beyond the edge of the screen, so I just have to be careful when I trace anything, make sure that they're all appearing inside the frame. All right, so we talked about subroutines, we talked about the invocation of a subroutine, the definition of a subroutine, and also what to do when we're at the end of a subroutine so we can continue execution where we left off, okay? So today, what we'll do is we'll start with a kind of, it can be confusing, okay? We'll start with something that can be confusing. And the whole idea of introducing something like this is really to see whether we have a good, clear understanding of the concept. Because it should not be confusing, but if it appears to be confusing, that means we're either overthinking something or we're misunderstanding something. We're missing something, okay? So here we go. We'll go ahead and define a subroutine. Okay, the definition of a subroutine starts with define sub. In this class, for pseudocode, so we define sub. We'll call this sub1. Okay, because I'm not. There's no particular meaning to the subroutine at this point. I'm just using it to illustrate, what to do when you invoke a subroutine. And in this case, we'll have a conditional statement inside the subroutine, and any construct that you can have in any algorithm, you can use it in a subroutine. Okay, there's no restriction as to what you can do and what you cannot do inside the subroutine. In this case, we have if x is less than 3, then we do something. We'll go ahead and say x gets x minus 1 first, and then we invoke sub1 from here. And if and define sub. And outside of the subroutine, we'll go ahead and say x starts with a value of 0. And then we'll go ahead and invoke sub1. Oops, I made a mistake here. This is supposed to be +1. Okay, there we go. All right, so we'll take a look at what this is going to do, or answer any questions that you might have before we actually trace the subroutine. Okay, I indented too much. This one and this one, they need to be. Okay, so here's the algorithm. And there's a particular name to this type of programming. When a subroutine is invoking itself, there's a specific name to to this type of subroutine. Do you guys still remember what it was called? Recursion. Recursion, that's exactly what it is. Okay. If you look at the curriculum of most programming classes, they don't talk about recursion until maybe data structure, which is our CISP 430. But recursion by itself is actually not a difficult concept to understand. In fact, I would use this as a test to see whether this class as a whole is understanding the concept of the invocation of a subroutine and returning it from a subroutine correctly. Okay, so we'll go ahead and take a look at this one, and then we'll trace it. Are there any questions at this point about the algorithm as it is right now, before we even start to trace it? No questions? Okay, so let's go ahead and get started. And here we have another sheet for the trace. Open up a new window. And stop me to ask questions, as soon as you think, okay, I'm not quite getting this, I need some explanation. Okay, so once again, this time we actually need a comments column, because we do have a condition to evaluate on line 2. So we have one column for comments. We have line number and X. These are pretty typical columns. X starts with an unknown value, and that's my precondition. No big deal here. I'm not sure how much you remember from what we talked about last Thursday, but the first line we execute when we have subroutine definitions is going to be the first line that is outside of the definition of a subroutine. And in this case, it's line 7. Okay, so here's line 7. It doesn't do anything too fancy or too difficult. It's just initializing variable x to 0. And then here comes line 8. Line 8 is to invoke a subroutine. In this case, there's only one subroutine in this entire algorithm. It's invoking sub1. When we invoke a subroutine, there are 2 things to do. Okay, and you will hear me say this over and over and over again. The first thing we have to do is to allocate a new column. In fact, we have to allocate the leftmost available column. And which column would that be? I kind of answered my own question. But column D, exactly, because column C is already used for variable x. So column D is the leftmost available column at this point. So I'm going to allocate it. I will label it as return line number so that we know what that column is used for. In that column, I'm going to store the line number of where I'm supposed to come back to when the subroutine sub1 is done. This is kind of new, because last time when we traced, we always return to a particular line. But in this case, because the invoke statement is the very last thing we want to do in the algorithm, where do we return to? We return to post, exactly. Okay. If there's nothing else to do, we just say return to post, which means by the time we get to post, then we're all done. That's the first thing you do when you invoke a subroutine. The second thing is easier. You just continue execution in the subroutine that you are invoking from the very beginning. Okay, so I'm going to emphasize that when you invoke a subroutine, you always start from the very beginning of the subroutine that is named in the invoke statement. We don't trace line 1. Okay, so line 1 of this algorithm, which is just the beginning part of the definition, we don't trace that. That really is just marking the beginning of the entire subroutine. But we can start with line 2. When you execute a conditional statement or loop or anything like that inside a subroutine, it is no different from when it is not inside a subroutine. Yes?
Once the subroutine gets invoked, then you go back to the first line. What was that again you were saying?
When you invoke a subroutine, you continue after you save the return line number using a new column. You always continue execution from the very beginning of the entire subroutine. You never go into the middle of a subroutine and say, I'm going to start here. You always start from the beginning of a subroutine. Now that's not conflicting with what we have talked about on last Thursday. It's just that I want to emphasize that, because now when you are invoking a subroutine from itself, that point becomes even more important. All right? Okay, so we start with line 2. Line 2 is the beginning of a conditional statement, and we have to evaluate x is less than 3. What do you think? X is less than 3 is true. Okay, well, and the conditional statement behaves exactly like a conditional statement, whether it is inside or outside of the definition of a subroutine. It doesn't change the behavior of anything. So we move on to line 3 because the condition is true. We have x gets x plus 1, so x goes from 0 to 1. And now we have line. Do you guys have any questions?
Oh, no, I was just explaining something.
Okay, all right. So now we move on to line 4. line 4 is invoke sub1 again. And guess what? We're going to do what we usually do when we invoke a subroutine. Whether it is inside the very same subroutine that is invoking, or from outside, or from any other subroutine, doesn't make a difference. Yes?
The X is outside of the subroutine.
X is what we call a global variable, which means there's only one variable X and is visible throughout the entire algorithm. So there's no problem referring to X anywhere. Okay? So now we can say, okay, what do we do when we invoke a subroutine? Well, the first thing we have to do is what? We allocate a new column. In fact, it is the leftmost available column. Go ahead. Sorry. Oh, I missed what you said.
Oh, sorry, I was about to say the leftmost column.
The leftmost available column, we allocate it. Very good. Okay, it is very important to be the leftmost available because we don't want to randomly allocate columns. We want to use a particular order. So in this case, column D is already in use. Okay, it is serving as a return line number for somebody. So now we have to allocate column E, and we label it the same way. It's return line number. And this time, where am I going back to when the invocation of sub1 is done? No, we don't trace line 5, remember. It's going to be line 6. Okay? So after line 4 executes, we always continue execution. In this case, on line 6, because we don't trace line 5. So the return line number is actually line 6. Is that part okay? Why the return line number is line 6 instead of line 5?
I don't get it.
When you're done inside a branch of a conditional statement, you continue execution with whatever statement is following the conditional statement. So it is the same thing here. When we are done with the invoke statement on line 4, we don't trace line 5 because there's nothing to do on line 5, and instead we continue execution on line 6.
What is there to do on line 6?
Well, there we are. When we get to it, I'll explain it. Okay? But that's where we will continue execution when this particular invocation of sub1 is done. Okay? Now, it is very important, okay, and most of you will probably forget what I said here, what I'm saying here. And the important part is there's only one subroutine sub1 here. But the very same subroutine can have multiple active invocations at the same time. Okay? There can be multiple invocations of the same subroutine at the same time. So I'm going to explain that later. All right. So are there any questions about this particular step here? On line 4, the first thing we do is to allocate a brand spanking new column, the leftmost available one, and then we use it to remember where to go back to, which is line 6.
Well, I'm just kind of confused. On the first one, you're ending on post.
Right.
And the second one, you're ending on 6.
Because this is where it happens. So when this is done, we have to continue here. Because there's nothing after line 4 in the conditional statement. So when we are done with line 4, we get out of the conditional statement, and then the only thing left to do is on line 6. Because the end of a subroutine has something to do too. Okay?
What about the first one though?
The first one? What do you mean by the first one?
So he was asking, it was just like the
On line
second
8?
one- yeah, the second one you went to line 6. So the first one you went to post.
Yeah, because post is right after line 8. There's always an implicit line here, which is our post. Is that okay? Post is really just an imaginary line in a program or in an algorithm that marks the end of the entire algorithm. So it's always after the very last line that is displayed in the algorithm. Are we doing okay or not? The most important part is, am I doing anything differently this time on line 4 when I invoke sub1 compared to what I have always been doing, in the previous class? No? Yes? You guys still remember our discussion on last Thursday? Yes? No. Well, 5 days in between, and that's what happens, right? Okay, I'm gonna pass the row sheet. Okay. I'm gonna suspend this, and we'll use a new example first, just to refresh your memory of what a subroutine is. Okay. And by the way, you're supposed to have studied this too, in the notes. Okay, so I'm gonna go over this relatively quickly because we have done this already. But it's gonna serve a purpose too, so I'm gonna do it. Does that look kind of familiar to you? It should, because it's almost identical to the example that I used on last Thursday. I'm going to save the time that I would otherwise, use to explain, study habits. Especially when the lecture is online on YouTube. All right, so here's x, starting with an unknown value. This is a precondition. On line 4, because it's the first line outside of the definition of a subroutine, we start with that one. X gets a value of 0. And then on line 5, we invoke a subroutine. When we invoke a subroutine, it's going to do two things. It will allocate the leftmost available column. In this case, it's column C. We'll label it return line number. It's going to remember where am I supposed to continue when line 5 is done, when the subroutine sub 1 is done. In this case, after we come back from subroutine sub 1, we have to continue execution on line 6. So we remember the return line number is line 6. That's the first thing we do when we invoke a subroutine. The second thing we do when we invoke a subroutine is to continue execution inside the subroutine. In this case, it will be line 2. Line 2 is just adding 1 to x, no problem. X goes from 0 to 1. And then on line 3, which is the end of a subroutine, we got two things to do as well. The first thing we do is to find the rightmost active return line number. Okay? And in this case, the rightmost active return line number is column C, which is the only return line number. We use that to tell us where we are going to continue execution. In this case, it's line 6, so we would put a 6 here. But at the same time, we'll say, oh, okay, now that we have used the content on line of column C, we don't need that anymore. And when we don't need that anymore, we'll deallocate it. And the way I denote the deallocation is to use the font effect of striking out. And now, from this point on, from row 7 of the spreadsheet on, that column C, is once again available because I'm quote unquote deallocating it. Line 6 doesn't do anything very special. It's just doubling the value of x, goes from 1 to 2, and nothing is after that, so we get to post. Okay, so this is pretty much as simple as it gets, when it comes to a subroutine. Are there any questions about this particular example? Okay, questions? Okay, I'm gonna hide this one and then go back to the one that we have currently, and I'm going to.
Actually, I've got a question.
Yes.
Can you go back to the other one?
Yep.
So if you had another invocation of that subroutine, say starting in on line 7, would you still use column C?
Yes.
As the rightmost, or you wouldn't use D?
You would not use D because let's
So
go.
once
Let's
you
do
close
it.
it out, you can actually use that column.
Yes, that's the whole purpose of closing it out so that you can reuse that column. So, if you want, it's not a bad idea just to put, it over here as well. So we have invoke sub 1 again here. So let's say that's the entire program. That means we're not quite at post. We're going to invoke it here. We'll once again allocate the leftmost available column. At this point, column C is available because we just deallocated it. So that means we'll reallocate column C for return line number purposes. But this time when we are returning to post because there's nothing after the invocation of sub 1. And then we continue execution in the subroutine starting on line 2. We add 1 to x. X goes from 2 to 3. We go to line 3. Line 3 has got two things to do. One is to look up the rightmost active return line number, which is this guy here. It tells me to continue execution at post. And once I use the value of the return line number, it is not of any use to me anymore, so it's time to deallocate it. And I'm just using this notation to say that, okay, from here on, the column is once again available. Yep.
So the first return line number was 6, that would be stop 2, or no?
That will be what?
That'd be unallocated 2, the first return line number 6.
This one?
Up one more. Like, would you put a slash to that return line number above 6? Where you were just at? The first return line number.
The first return line number is
Line
line
number
It's
6.
implied that it's not there anymore. He's inquiring why they wouldn't put a hash mark through the return line above.
You mean
line
here?
6. Yeah, that one, right.
Because we are just allocating it. In other words, the lifespan of this return line number is going from here to here. This is the lifespan. Okay, I'm going to use a background color to indicate the lifespan of that stuff.
Okay.
So
Okay.
This is pretty much showing the body of the subroutine.
Okay, hold on. Okay, let me clarify what you just said. Okay, could you say that again?
It's just going to be showing what the body in terms of the
The-
lines, and then when it exits out.
Okay, you need to clarify a little bit more.
In other words,
Which
for
row, which
someone-
column
So
are you referring to?
the highlighted.
The highlighted portion.
Yeah,
is-
is pretty much showing the body of the sub one,
Mm,
the invocation of sub one, and when it closes out.
it's indicating when column C is in use. When it is highlighted, it is in use. When it is not highlighted, it is not in use. That's what it's indicating.
Yeah,
Now
that's the same thing I was saying, just different one.
Okay. But it's basically indicating when column C is actually in use. So column C is in use when we are on line 5 here, when we are on line 2 here, and even when we are on line 3 here. But it is that line 3 that is deallocating it. So it is no longer in use by the time we get to line 6. You can see it's no longer highlighted. So by the time we get to line 6, column C is available. It's not in use. And that's why on line 7, when I have to allocate the leftmost available column, column C is once again available because nobody is using that column at that point.
And just, out of curiosity, is this column like on an actual programming level, like memory allocation, or?
Every column except for the line number and the comments in this class correspond to some kind of memory location. Yes, that is correct. Okay. Now you might think this is like way over complicated, especially those of you who already know how to what a subroutine is. But this is actually preparing you for cisp300, the assembly programming class. If you can retain what you learned in this class, because you have to take 360 first, right? So if you can retain what you learned in this class, by the time you get to cisp300, it will be the same stuff again, except the terms will be different. Okay, we'll be talking about the stack pointer, return address instead of return line number, that sort of thing. But it's the same concept. All right? So it is important. Okay, this is really quite important. All right, so do we have any other questions about this example? When we have invocations of a subroutine from outside of the subroutine itself, but it's doing it twice. Go ahead.
I was like, did you say assembly language was after this? I didn't understand. I didn't hear you earlier.
I said, this stuff will appear again in cisp300, which is the assembly language programming class.
Okay.
It will be the same concept. They will just have new terms or new terminologies by the time we teach, but by the time we are in that class. So it's not something that is just invented for this class just to make your lives miserable. It may be doing that effectively, but it is going to be useful later on. Okay, is that okay so far? Okay. So just remember, when we talk about this one, which is a little bit more confusing than the other one. Okay, I have to hide the one that I'm not using, so I don't confuse myself. This one I don't need, and this one I don't need. So now we are back to the recursive example. And I'm going to erase this part here just to redo it, okay? After line 3, we continue on to line 4. Line 4 is to invoke a subroutine. Remember what we need to do when we invoke a subroutine? 2 things. Allocate the leftmost available column so that we can remember the return line number, right? The leftmost available column is now column E. So return line number is allocated at this point. But in order to return, or which line we are supposed to continue, is on line 6 in this case, because after line 4 is done, we don't trace line 5. Okay, in this class we do not trace end if or end while, and that's why we don't make line 5 the line to continue onto, but we make line 6 the line that we are going to continue once the invocation is done, because line 6 actually has something to do, because we just demonstrated that in the previous example. Okay? But at this point, I'm not executing line 6. I'm moving on to the subroutine that I'm invoking, which is sub1. Now, the fact that I'm invoking sub1 from inside sub1 doesn't change that behavior whatsoever. So what do you think is the next line that I will execute?
2.
Back to line 2. All right. So back to line 2, it's going to do the same thing as last time. It's going to compare x to 3. X is now 1. 1 is less than 3 is once again true. Then we move on to line 3. We add 1 to x. X goes from 1 to 2. Then we go to line 4 again. What do we do on line 4? What do we do when we invoke subroutine sub1? I'm certainly hoping that this is starting to be boring. We allocate the leftmost available column to remember the line that we are going to continue on after the invocation is done, which is on line 6. Same thing, right? I mean, it's exactly the same mechanism every time we invoke a subroutine. There's nothing changed here. And then we continue execution in the subroutine that we're invoking. In this case, because we're invoking sub1, we start execution at the beginning, which is on line 2. Is that okay so far? Okay, on line 2, what do? Same old thing. We compare x to 3. X is less than 3 is true, basically one last time. And then on line 3, because the condition is true, we get into the branch on line 3. On line 3, we add 1 to x. X goes from 2 to 3. And then on line 4, same boring stuff again. We allocate the leftmost available column to remember the return line number. And once again, because the invocation is on line 4, we continue execution on line 6. Okay? Nothing has changed. And then we continue execution at the subroutine at the very beginning, which is on line 2. And this time, x is less than 3 is finally false. All right. Okay, well, if the condition is false, we don't execute line 3 or line 4. We don't trace line 5. So what is the next line?
6.
Line 6. All right. What do we do when we encounter end define sub? There are 2 things to do. First thing, look up the rightmost active return line number column. Holy smokes, we have 1, 2, 3, 4 active return line number columns. But remember what I said? The rightmost one. So what is the rightmost one? Column G. It tells us to continue execution on line 6. Okay, fine. Okay, no problem. Okay, it looks kind of confusing because we are going from line 6 to line 6. But you know what? It's okay. We are just, quote unquote, blindly following the mechanism. And once we utilize this line 6 from here, then we have no use of this column anymore. So now we say we deallocate that column, which basically is just, in this class, I'm just, putting a strike through, on the label, so we now indicate column G is once again available if I have another use of that column later on. And then we continue execution on line 6. Again, what do we do on line 6? This is starting to sound like Pinky and the Brain. Brain, what are we going to do tonight? Same thing we do every night, right? Try to take over the world. Okay, so what do we do on line 6? Come on. Line 6 is undefined sub. We got two things to do. Look up the rightmost active return line number. In this case, it's not column G anymore. Column G is now gone. We just deallocated it. So the last one, or the most recent one, or the rightmost one that is active is now column F. Column F tells us continue execution on line 6. Fine, we'll continue execution on line 6, but then we have to deallocate that particular column. Right? Okay. Now we keep going, right? Now we are executing line 6 again. What do? Same thing. We look up the rightmost active return line number. Column F and column G are both gone by this time, so column E is the rightmost one. It tells us continue execution on line 6. All right, we'll do that, and then we deallocate column E. Now we are on line 6 again. But this time is a little bit different because this time we look up the rightmost active return line number, which is now column D. Column D tells us something a little bit different this time. Continue execution at post. Fine. And then we have no use of column D anymore. We deallocate column D, and then we continue on post, and we say, oh, we're done. Finish line. Are we doing okay so far with this concept? Maybe, okay. Just remember, the mechanism of invoking a subroutine doesn't change. The mechanism of returning from a subroutine doesn't change. Whether you're invoking from outside of a subroutine, from inside the very same subroutine, it's doing exactly the same thing. All right? Now, if I want to show you the lifespan of when a column is being used, then it will be like this. For this one, it is from row 12 to row 20. For this one, it is from row 8 to row 21. And this one, column D, is almost for the entire duration of the program execution, but not quite. Are we doing okay so far? In terms of highlighting, when a particular column is in use. What about column C? I mean, column C is kind of a column that is in use too. So exactly when is it in use and when are we freeing it? In other words, when is it deallocated? It's always in use until the end of the execution of the program. It is not allocated on the fly. We just start to use it from the very moment we start executing the algorithm. All right. Does this go ahead.
So if X did not have an unknown value, you wouldn't start from 7, you just start from 2?
If X
did not have an unknown value?
Okay. We still start execution on line 7.
Yeah.
Because line 7 is still the first line outside of the definition of a subroutine. That's basically the rule.
Okay.
Because you're not calling it. Because you're not calling it. It's calling subline.
Well, from line 1 to line 6 is the definition of sub1, but we don't do anything about it until somebody is actually calling for the subroutine. Yep.
Why do this instead of just put a loop in subline?
That's a good question. I'm really glad that someone is noticing, hey, this smells like a loop, but it's not a loop because it doesn't say anything about while or repeat, but yet it is doing something over and over again. So it has attributes of a loop, but it's not a loop.
Is it to save line space?
That would not be the only reason to do it. There are programming languages out there that has no loops, but it has conditional statements and subroutines.
Oh.
Yep.
Is it so that you don't have to like rewrite the loop over and over? You just write invoke sub one when you need it? Because you need it in multiple places?
That's a good reason to use a subroutine, but I think what he's asking is we could have done this with a loop,
Right.
and why are we not using a loop instead?
Yeah.
So that's a good question, and your answer is valid as well. Subroutines are useful because we want to reuse the same code from multiple places. Okay, but the main reason why we are doing this, I'm so glad that you asked the question because I was just about to answer that question with an example. Okay, so the example is like this. Okay, it may look and sound like it is unrelated to what we are talking about here, but it is. Okay, so let's talk about factorial. Okay, we talked about factorial. The first time we talked about factorial in this class is when we talked about the NP complete problem, the traveling salesman problem, the pizza delivery problem. Remember that? Okay, so factorial is no mystery. Okay, 5 factorial is 5 times 4 times 5 times 4 times 3 times 2 times 1. Okay, well, it's not mysterious at all. But when you look at this form, and let me just regroup things a little bit here. Okay, well, tag, we know that. Okay, it's called the associative property of multiplication, right? I can regroup multiplication any way I want, and as long as it's a sequence of multiplication, it will still come to the same conclusion, the same product. But what we are looking here is, hey, 4 times 3 times 2 times 1, I think I have another name for that. Don't you think? Because I can now say that it is 5 times 4 factorial, because 4 factorial is exactly 4 times 3 times 2 times 1. Cool. So that means I can express a number's factorial as a product of that number times that number minus 1, the whole thing factorial. In other words, it seems like if you give me any number n, the factorial of n can be expressed as n times the factorial of n minus 1. Right? Well, you can do it like this unless n has a special value. You can keep doing this because if you keep doing this, n will become smaller and smaller. So we have to end up at some point and say, but what about 0 factorial? Oh, okay, with 0 factorial, we cannot say it's 0 times the factorial of -1 because 0 times anything is 0. 0 factorial is actually defined to be 1. That's a definition. So this way, we can redefine factorial in a, guess what, recursive way. Because the definition of factorial depends on factorial itself. Okay? But that still doesn't explain why we are using recursive definition or recursive subroutines when we could have used something that is non-recursive. Okay, so it's time to call for another example where recursion is actually useful. It's called Fibonacci numbers. Okay, now Fibonacci numbers is like this. Okay, it's a sequence from 0 to 1, 1, 2, 3, 5, 8, and so on. And when you look at the definition of the Fibonacci series, f of n is expressed as f of n minus 1 plus f of n minus 2. And you can keep doing this or breaking it up like this until you get to f of 0 is defined to be 0, f of 1 is defined to be 1. Yep.
I think you just answered my question. I was assuming it wouldn't stop, the program wouldn't stop unless you gave it a positive integer as its exit, right? Or else
In the algorithm, in factorial or the...
Factorial and, because it's
Yeah, factorial only
and
works for...
less than, I mean, equal to or less than, right? So it would
Yes.
keep going.
You only use natural number for factorial because it's really answering the question of how many permutations there are when you're given so many objects. When you're given 0 objects, there's 1 permutation, which is nothing, right? How many ways can you arrange nothing? 1 way. That's the definition of why 0 factorial is 1. If you give me one thing, I can arrange it exactly 1 way. So that's 1 factorial. So factorial can be seen as how many ways can you arrange something where the ordering is important. And that's why negative numbers don't make sense, because you cannot give me a negative number of objects. It has to be a countable number.
So essentially, you have to give the program a reason to exit, and you have to give it 1, right? A value of 1. Once it reaches to 1, then stop the program. Or else it just
Technically, you have to reach 0, because the definition is 0 factorial is 1.
Okay.
So even 1 factorial is defined as 1 times 0 factorial.
Yeah, okay.
Yep. Okay, so this is one kind of reason why we have recursion, but there are other reasons as well. Okay, there are other reasons why we use recursion. Do you think binary search can be done in a recursive way? In other words, can I break up a large problem into a smaller problem, but it is very similar in nature? In binary search, it is. Okay? The original problem is I have a huge array of numbers that is sorted. In one step, I can break it into 1/2, and then what do I do with that remaining half? I apply the same method to it. So it can be done in a recursive way, but that's still not answering the question that you're asking. We can still do it in a loop. Why use recursion when we can do it in a loop? Here is something that is not so easy in order to use a loop to do it. I'm going to use the file manager for this purpose, and I will pick something that has a lot of subfolders. So I will go to the Windows folder here. Oh, I forgot to change my password. All right, so here is a good example of why recursion is useful. Now, to most of you who have not used command line stuff before, if you want to remove a folder, you just select the folder and then you press the delete key and you're done, right? But to the computer system, it's not really quite that simple. The only time you can remove a folder is when it is empty. Okay, that's a rule. Okay, it's a rule that you cannot remove a folder unless it is empty. So when you try to remove a folder, you cannot just say, oh, I'm just going to press the delete key, because internal to the computer, it has to say, okay, I have to make sure that this folder has no content before I can remove the folder. Great. Because now, if I look at this in a, let's see if this is, nope. I'm trying to see if it has a view where I can view it in a different way. It doesn't seem to have that. But that's okay, because I can just open up a new tab for this. Okay, so here's a new tab looking into documents and settings. Oh, I guess I cannot delete documents and settings because it has got subfolders. Okay, is that making any sense so far? That I cannot remove documents and settings because of the rule that I cannot remove a folder that is non-empty. So out of these subfolders inside documents and settings, I'm going to pick on 152 user first. Okay, and I will say, okay, I'm going to remove this folder first because I want to remove all the items inside documents and settings in order to make that folder qualify for being deleted itself. So I would pick one and say, can I remove you? Okay, now we have 152 user, and bummer, it has got subfolders too, right? So I cannot remove 152 user at this point because it has got subfolders. I'm going to pick up the first one and say, can I remove you? App data. Okay, open a new tab. No, I cannot quite do that yet. Can I remove local? No. Can I remove Adobe? No. Can I remove AAM updater? No. Can I remove 1.0? Getting close. Okay, because this time I don't have any subfolders anymore. I can deal with individual files. So the computer system would actually go here and say, woohoo, we don't have subfolders anymore. I can delete files. So once these 3 files are deleted, okay, then I will go back up one level to here. Actually, to here. And because that folder is now deleted, I can now delete 1.0, right? I can delete 1.0, but 1.0 is the only thing in AAM updater. So now AAM updater itself is also empty. Then I go back up to Adobe, but then I would just have removed this one folder. Now it's time to move on to Acrobat itself and then repeat the whole process. Does that smell like recursion to you? In order to remove a folder, I'm applying the same technique over and over again. Okay? And in this case, it's really difficult to turn it into just a loop, because a loop doesn't have the ability to quote unquote backtrack. Okay? You remove something, but you have to get back to a previous point and say, what else was I supposed to do? And that you continue to do what else you're supposed to do. Okay? So that's one application of recursion that makes it far more expressive compared to loops. Now, given that, you also have to keep in mind, because this question will pop up, again and again. Whatever you can express using recursion, you can also express exactly the same algorithm using a non-recursive way. And vice versa is true as well. Okay, whatever you can use a loop to express, you can always use recursion to express it. In other words, expression of loops versus recursion, they have exactly the same expressiveness. Okay, any algorithm that can be expressed using one can be expressed using the other one. It's just a matter of which one is the proper tool to better implement that algorithm. Okay. Any other questions? No other questions? But in this class, I'm using recursion, to make sure that people understand what subroutine is about. Okay, how do you invoke a subroutine, and how do you return from a subroutine? So I'm going to close this one before I accidentally actually press the delete key, because that would be bad. Tomorrow somebody's going to call me if I did that. Because those files or those folders are not supposed to be deletable. The fact that I can delete them, there's only one person who can delete those things other than the technicians in the lab. They know who that person is. All right. So are there any questions at this point about calling or invoking a subroutine, and also how to return from a subroutine? Okay, any questions? If there are no questions, I'm going to write factorial using recursion. Okay, so we'll go ahead and write that in a new spreadsheet. So this time we'll say define sub, and this time I'll give it a name because I know what it is supposed to do. It's supposed to do factorial. Now, when you write a subroutine in a recursive way, you have to ask yourself, if I'm given a particular problem, can I solve it by myself? Okay, that's the first thing you want to ask is, can I solve this problem by myself? If not, then the question is, how do I break it up into something that I can solve and the invocation of the same subroutine? In other words, break it up to a sub-problem that has a similar nature and a operation that you can actually perform. That's the way you think about recursion. So in the case of a factorial, what you are supposed to do is you're given a number n, and you're supposed to find n factorial. That's what you're supposed to do. So you have to break it up into cases, and you say, well, it depends on the value of n. If n is a particular value, I know the answer. But if n is anything other than that value, I need to kind of defer to another invocation of factorial, plus something that I can do in order to come up with n factorial. Is that making any sense? Okay. It's going back to the example that we just looked at, or the notes that we just looked at here. If the number that you need to find a factorial of is 0, then you can just answer the question and say, yep, I know the answer is 1. I do not need to figure out the factorial of somebody else. On the other hand, if n is anything other than 0, then you say, well, in order to figure out the factorial of n, I can do this part, no problem, because I know what n is, and I also know what multiplication is, but I'm going to defer to somebody else to figure out what is n minus 1 factorial. Okay, so that's how you think about recursion. So in this case, there are distinctly two possible cases here. One is when n equals to 0, then we'll do things in a certain way. And then the other way is to say, well, what if n does not equal to 0? In this case, n has to be non-negative. Okay? So we'll try to figure out what we do here. Well, if n is 0, I know the answer is going to be 1. Okay? And I'm going to use a variable r to represent the answer. And I'll just say, okay, the answer or the result is just 1. No problem, we can do this. And I'm going to do some indentations here because it's just easier to read when we have indentation. The else case is corresponding to when n is not 0. But n is non-negative, so when n is not 0, it has to be 1, 2, 3, and so on. So what I need to do in this case is to say, I'm going to break the problem up a little bit here. Okay? I'm going to decrement the value of n first. Okay? And then what I'll do is I'm going to ask somebody else to figure out what is the factorial of n minus 1. So I'm going to insert a row here. Who can figure out factorial?
Same routine.
The subroutine that I'm writing, right? Okay, that's fine, because I'm just going to say, okay, I know somebody who can solve this problem. It is factorial. When factorial comes back, it will have the result in R. Right? Because that's its job. The job of the subroutine factorial is you give it a numerical value n, and it gives you the result in R. So by the time you get to line 7, factorial would have figured out the factorial of n minus 1, because I just change n to n minus 1, so it would have that result. But that's not exactly what I need, because I need to figure out the result of n factorial, which is n times the factorial that is just returned to me. So it appears that this is what I need to do, but that's not going to work because n has already been decremented by 1 at this point. So you have two approaches here. The first approach is to, well, I would say there's only one approach. Okay, let's just limit ourselves to one approach here. So the first thing you want to do is to undo what we did a little bit earlier by adding 1 back to n. Then we can just say r is n times r. Because the r on the right-hand side of the assignment statement is coming from the factorial on line 6, which is the factorial of n minus 1. But by this time, n would be back to its old value because I just added 1 back to n. So we would actually figure out what is n factorial using this particular expression. And you know what? That's it. That's n. That's factorial in a recursive way. And I'm going to do all the correct indentation first and define sub. And in order to make this subroutine work, we have to give n a particular value. We'll make it maybe 3. Okay, 3 is a little bit more fun. Invoke factorial, and we'll see whether this program works or not. We'll trace it. All right. Are there any questions about the algorithm itself? Ooh, pick me, pick me. R is not initialized. Isn't that going to be a problem? I mean, what if we hit line 8 before we hit line 3? Then R is uninitialized and we are going to have problems. Well, we'll see. Okay. New window. And we do have conditions to evaluate. In this case, it is on line 2. We got line number. And we have 2 variables in this case that are visible throughout the entire algorithm. N and R are both visible throughout the entire algorithm. And the precondition is neither starts with any specific value. We start on line 11 because that is the first line that is outside of the definition of a subroutine. We only have one subroutine definition here. but it's the first line that's out of it. So n gets a value of 3 to begin with. And then we get to line 12. Line 12 is the invocation of a subroutine. In this case, it's factorial. So we do all the boring stuff that we have been doing before. We allocate the leftmost available column. In this case, it's column E. We label it return line number, and we say, when we come back from the invocation of factorial on line 12, we continue to the finish line. There's nothing after this line, so the return line number is post. Then we can continue execution inside the subroutine, which is on line 2. So now we continue execution on line 2. Are we doing okay so far? Okay. On line 2, we have a comparison. We try to check to see whether n equals 0 or not. No, it is not, because n has a value of 3 at this point. So we go to the else branch here, which starts on line 5. Line 5 is just decrementing the value of n. It goes from 3 to 2. Then we go to line 6, which is the invocation of factorial again. Fine, we'll go ahead and allocate the leftmost available column. In this case, it's column F. And then we have to remember which line that we have to come back to continue execution when the invocation of factorial on line 6 is done.
It's 10.
No.
Seven.
Line 7. There's stuff after the invocation, right?
Oh, good. Okay.
Okay, so we have to continue execution on line 7. So we just say, okay, when we come back, we have to continue on line 7. And once we remember how to continue execution after the subroutine is done, we can actually go into the subroutine on line 2. And we ask the question, it is false because n has a value of 2 at this point. We go to line 5 again. We subtract 1 from n. It goes from 2 to 1. Then we go on to line 6. We invoke factorial again. Same old stuff, right? Invocation means allocate the leftmost available column, which is column G in this case. Call it return line number, and then write down where we are supposed to continue execution after line 6. It's going to be line 7 again. And once we remember all that stuff, we continue execution from the beginning of the subroutine that we're invoking, which is on line 2. N equals to 0 is false for the last time. And then we go to line 5. We decrement n by 1. So it goes from 1 to 0. And then we go to line 6. We invoke the subroutine again, which is now getting really boring. Return line number is allocated on column H because that's the leftmost available column. After line 6, we continue on line 7. So let's remember that. And then we continue execution from the beginning of the subroutine, which is on line 2. N equals to 0 is true now, okay? And this is a good time to kind of use this little trick here so we can still see the labels of these particular columns by scrolling these two different parts of the spreadsheet separately. Okay, so on line 2, the condition is true. We go to line 3. R finally gets a value, which is 1. Okay, which is correct. I mean, we know that by definition, the factorial of 0 is 1. So factorial has done its job. It's time to return. After line 3, which is the only thing it has to do in the then branch, we get out of the entire conditional statement. Then we get on to line 10. On line 10, it is the end of a subroutine, so we have to continue execution based on what return line number is going to tell us. We have to look up the rightmost return line number that is active. In this case, it's column H. Okay, column H is telling us that we have to continue execution on line 7. Okay, so we'll go ahead and write down 7 here, but then we also have to remember to deallocate the column. It is line 10 that is deallocating the column, so that's why we have to put it here, and then use format cell strike through to indicate that at this point we have deallocated column H. Now we are executing on line 7 again. What does line 7 do? It's adding 1 to n, right? N is column C. It has a value of 0 at this point. Now it's back to 1, and then we move on to line 8. Line 8 is just multiplying n and r at this point. N is 1, r is 1, 1 times 1 is 1. Okay. Now, before we move on, we have to kind of double check and make sure that it makes sense. Because what this is saying is the factorial of 1, which is n, is 1, which is r. Is that right? If you give me one thing, there's only one way to arrange it. Okay, makes sense. Okay. After line 8, we get out of the conditional statement. We continue on line 10. Line 10 is saying, okay, we are now at the end of a subroutine. I need to know where to continue execution. Let's look up the rightmost active return line number. Now it is column G because column H is now deallocated. I cannot look up column H anymore. So column G is the rightmost active one. And it tells me to continue execution on line 7. So here we come, line 7. And on line 7, we add 1 to n. N is currently 1, so we add 1 to it, it becomes 2. On line 8, we compute the product of n and r.
Don't you have to deallocate?
Nope.
On line 23, column G.
You mean on this line 10?
Yeah.
Yep, I forgot. So on this row, we have to deallocate return line number because we just did a return. Good job. You caught me. That's good. That really is a good indicator. You say, well, on line 10 we're supposed to do that. Good job. So on line 8 we compute the product of n and r, which is 2 times 1, and then we store it back into r. So r is now updated to 2. So nothing really is interesting at this point, but it is correct. Okay, if you give me 2 things, I have exactly 2 ways to arrange it where the order is important. Because if you give me 2 objects, A and B, I can arrange those 2 things as AB, and I can rearrange it as BA. Okay, but those are the only 2 permutations that I can do with only 2 objects. So we get onto line 10 again. This time we look up the columns, and column F is now the rightmost active column with a return line number. It tells us to continue execution on line 7. So we'll go ahead and put a 7 here. And also at the same time, this is the right time to deallocate column F. And now we continue execution on line 7. Line 7 is adding 1 to n. N goes from 2 to 3. On line 8, we compute the product between n and r. 2 times 3 is 6. So we put a 6 here in r as our result. If you give me 3 things, there are 6 ways to arrange them. Does that make sense? If you give me A, B, and C, there are exactly 6 ways to arrange things where the order is important. Well, let's double check and make sure that that actually makes sense, right? You have A, B, C, okay? Now, the way I solve this problem can also be recursive. Because I can say, let's fix A, and then you say, okay, you give me B and C, how many ways do I have to arrange B and C? Well, if you give me B and C, I can arrange those things as A, B, C, and then C, B, and they all start with A. But then I'm done with everything that starts with A. If I start with B, the remaining items are A and C. How many ways can I arrange A and C? Exactly 2 ways. So we have BAC, and then we have BCA, and now we have the third thing that can potentially be the first one, which is C. But once I take C as the first position, the second and third position can only be A and B. So I have 2 ways to arrange A and B. We have AB, and then we have BA. And those are the 6 possible ways to arrange 3 items. Okay? And that's why it's 6. That's why 3 factorial is 6. Because once you have 3 choices for the first item, but once you have selected the first item, you only have 2 choices for the second. But once you have selected the first and the second, you only have 1 thing left as the third one, which means you don't have a choice. So that's why it's 3 times 2 times 1. All right, so we are pretty much done here. After line 8, we get to line 10. Line 10 is looking up the rightmost active return line number. In this case, it's column E. It tells us to continue execution at post. And then we have no use of that column anymore. So on line 10, we're deallocating that column. And then we get to post, which means we're at the finish line. We have the result all computed. 3 factorial is 6. So are there any questions about this particular trace? Doesn't it have the same flavor as the other one, the first one that we did? except this one actually has some computation involved in it. Are there any questions about this type of factorial? Yep, go ahead.
Just applying it to a real programming environment. Is there like a basic guideline as to how much you can actually put in one? Like if you're calculating a factorial, you have a certain computer with a certain amount of memory. Is there like a certain way you could calculate how big of a number you can actually?
Well, in this case, every time you have, every time you increase n, right, exactly. So if you're computing 3 factorial, we are using up 4 columns, right? So the number of columns that you're using is n plus 1 in this case. If you want to compute 100 factorial, it would use 101 column just to store the return line numbers.
Is there like for most programming languages in terms of actual memory
Mm-hmm.
to use? Or let's say I'm calculating recursively, searching all the files in a computer.
Okay. All right.
So is there like a certain point where it's going to hit the wall and then out?
Yes, in theory, yes, you can always hit a wall, okay? Because in the case of searching for a file, let's say you're looking for a file with a particular content in it, okay? A lot of utility program has a -r option, which means it's going to recursively search for that particular pattern. So yes, you can potentially hit a limit and say, okay, we have the depth of the last file is too deep, and we run out of memory to get to that one. Okay, it is possible, but the question is, can you realistically get to that bottom? Okay, because in the case of searching for a file, the number of how much memory you are consuming is proportional not to the number of files involved, but to the depth of the deepest file in your structure, in the folder structure. Okay, and most modern computers would allocate megabytes, at least megabytes of memory to to what we call to do this kind of thing, which is basically saying you can literally have hundreds of thousands of levels of folders way before you can hit that limit. So realistically speaking, probably not. Okay, but yes, you can artificially create a file structure where you just create subfolder, 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 and you're just testing when the program will crash. Now, given that extreme example, if you do it in a non-recursive way, it will still hit a limit of some kind, because you still need a way to remember, I have searched these subfolders of this folder already. It's now time to move on to the next subfolder. So you still have to allocate memory. It's just a matter of, are you pre-allocating something and you can check for the limit, or are you allocating on the fly and hit a limit and have a harder crash? So that's really your choices. Okay, you're gonna run out anyway. It's just a choice of whether it is crashing or whether it is just giving you a more friendly message and say, I'm only capable of searching 65,536 levels, and your file structure has more, it's deeper than that. So that's a good question. It's a valid question, and in certain cases you do want to avoid the use of recursion, like a space probe, a probe that lands on Mars. You probably don't want it to use recursion. Any other questions about? Yep.
Are the variables E, F, G, H reusable, usable while they're alive?
When they are in use, you cannot use them.
No, what I mean, refer to them in another portion of the code.
When they are deallocated, no, there are no ways to actually refer to columns E, F, G, and H in this case. Not in this case. Okay. When we start to use local variables and parameters, then yes, in certain cases, you can refer to the content of a column using a name of a parameter or a local variable. So are there any other questions about invoking a subroutine and what we do at the end of a subroutine, which is called returning from a subroutine? If there are no questions, we'll introduce the concept of a local variable. Let's go ahead and take a look at the notes here, because I want to show you where you can find information about it. So we are pretty much done with section 3 here. Okay, section 3 just talks about what do we do when we are invoking a subroutine and what do we do when we are returning from a subroutine. We are done with section 3 already. So the next topic we're introducing is section 4, which talks about local variables, and then we'll talk about local variables in a recursive way. Okay, so we'll go ahead and start with local variables in this case. Local variables is a little bit easier to explain why we need that. So I will start with, yep.
Recursive would that be also synonymous with nested?
In a way it is nesting, but it is also, it's not nesting as in you have a statement inside another statement. It is nesting in the sense that you have levels of invocations of a subroutine. Okay. All right, so what we'll do here is I'm going to use a very not so smart way to do multiplication. Okay. So we'll say define sub, and this one is just going to be n here. Okay. Okay. So I'm doing multiplication in a not so smart way because it is going to look like this. I'm going to say while okay, I have an iterator called I, starts with 1, and I'll say while I is less than n, the result, which is r, is going to be r plus 1, and while. Okay, and define sub, and we'll just go take a look at this not so smart subroutine. Oops, that's not what I want to do. I want to do indentation, but I accidentally used the other tool. Let's see if I can just delete content. Control Z. Yeah, that would do. Oh, it removed the indentation too. Okay, there we go. Without even tracing it, if r starts with 0 and n is 5, what would r be when this is all done? Okay, let me fix this first. This would be actually correct. Okay, so we start with, okay, let's say r starts with 0 and n is 5. We run through this algorithm exactly once. What do you think r becomes when we return from the subroutine? Exactly 5, right? Because it will go through the loop exactly 5 times. Each time is adding 1 to r, so r becomes 5. Okay. So it's just, basically it's just adding n to r. It doesn't do anything useful. In fact, let's go ahead and name it here. Add n to r. Wow. Okay, we need a subroutine to do that. Really? Okay. So now we want to define multiplication. Okay. So we want to say, r as product of n and m. Okay. Well, I'm going to use the same dumb approach here. I will say I is 0, but this time while I is less than m, we'll do the following. Hey, I know who can just add r to n, so I'm just going to invoke that subroutine here. So we'll say invoke add n to r. I gets I plus 1, and while, and define sub, and that should get the job done, right? I mean, that should be able to compute n times m and then store the result in r. So we'll go ahead and change the indentations a little bit. And outside of the definition of the subroutines, I'm gonna initialize n to some value. I would say n is 2, m is 3, r starts with 0. I invoke r as product of n and m, and I wanted to compute n times times m in this case. Yep.
Don't you need to increment I in the while loop 3?
Yep. You're right. I forgot that. Otherwise, it becomes an infinite loop.
Yeah.
See, this is my favorite mistake to make in programming. You will find yours. We all have favorite mistakes. This one is actually easy to catch because what do you think happens when the program runs? It's an infinite loop. Infinite loops are pretty easy to tell because your program is just not coming back when it's supposed to. But it is, it is my favorite mistake. So you will probably catch it a few more times before the end of the semester. All right, so here's my algorithm. Question is it going to work? Well, let's trace it. Okay, it's not going to work, but we want to find out why it is not going to work. It's not going to work not because it is not the smartest way to do multiplication, but because of a problem, the way that I'm using the variables. Okay, we have 3 minutes, but it's just enough time to illustrate why this is going to fail. So we have comments, we have line number, we have 3 variables in this case. We got n, m, and r. And the precondition is we don't know anything about any one of the variables. Starting on line 15, n gets a value of 2, m gets a value of 3, and on line 17, r gets a value of 0. And then on line 18, we invoke the subroutine. Okay, we know the drill. Okay, we allocate the leftmost available column to store the return line number. In this case, it is post because there's nothing after line 18. Then we continue execution in the subroutine, which is on line 9 in this case. Here's I needs its own column. So here's I. I start with a value of 0 here. And then we get on to line 10. I is less than m is true because m is 3, I is 0. And then on line 11, we are invoking another subroutine. We allocate the leftmost available column. We remember where we are supposed to go back to, which is line 12 in this case. And then we continue execution in the subroutine that we're invoking. In this case, is on line 2. Line 2 is reinitializing I to 0. For those of you who are feeling kind of uneasy at this point, there's a good reason, okay? Because it is the same variable I. But it doesn't seem like any harm is really done at this point because I is really just getting the same value again. 0 is being reinitialized, okay? So it doesn't seem like it's doing any harm at this point. Then we move on to line 3. I is less than n is true because n is 2. Then we go to line 4. R gets incremented by 1. And we go to line 5. I gets incremented by 1. And you probably should be feeling really uneasy at this point because what about that I that we initialized on line 9? Okay, what about that 0? It's gone now. Okay, and then we get to line 3 again. I is less than n is still true. Then we go to line 4, we add 1 to r goes from 1 to 2. We go to line 5, we add 1 to I goes from 1 to 2. And then we go back to line 3, I is less than n is false because n is 2, 2 is less than 2 is false. We get out of the loop, we end up on line 7. We know how to return from a subroutine. We look up the rightmost active return line number column, which is column H. It is telling us to continue execution on line 12. That's fine. And then we deallocate that column at this point. So we'll just go ahead and copy and paste it, and then change it to strike through. No problem, right? Now we're back to line 12. Line 12 is just adding 1 to I. Oh, which I are we talking about? There's only one I on column F. It is now 3. We go back to the beginning of this loop, which is on line 10. I is less than M is also false now. It is not supposed to. I'm supposed to go through the loop here exactly 3 times. But I went through it exactly once, and it's time to get out. Okay? And because it is false, I'm getting to line 14, but at this point I know the algorithm is incorrect already, okay? The algorithm is incorrect. What is the source of the problem? Why am I getting into this problem?
Sharing one variable.
They're sharing one variable, okay? The variable I is what we call a global variable, which means it is visible from anywhere within the algorithm. But because of that, the same variable I that I use in R as product of n and m is also the same variable used in add n to R. And that's why there's an interference, okay? And someone is going to say, but I am smart, I have a solution to this. Let's rename one of the variables to J. Right? That's the easiest solution. Okay? You just change, let's say the one from line 2 to line 5, change all the references to I to J, and we solve the problem. What if you have 50,000 subroutines? You run out of all the A to Z. Okay? How can you be sure that a particular variable used in one subroutine is not used by somebody else? I'm smart. I know exactly how to do that. I use the name of the subroutine as a prefix. So now we have a variable called add n to R underscore I. We have another variable called R as product of n and m underscore I. So now they're distinct, for sure. What if I have a typo somewhere in the program and I accidentally use the wrong prefix? Is the compiler going to tell me and say, hey, that's not supposed to be here? No. It's going through the same code. And what are the chances that I will spot it? Almost 0. Okay? So in addition to go to being the G word, now you have a second G word, global variables. Okay? We try to minimize the use of global variables for that reason. Okay? When we come back on Thursday, I'll show you the proper solution.
Would the proper solution include an array? Would the proper solution include an array?
No, the proper solution is to use local variables. So each one has its own I and is not visible from the other guy.
Oh, okay.
Yep. In fact, it's not visible from another invocation of the same song.
So I know that this is supposed to be wrong, but I was able to get out the first 2 sheets. Did I do something wrong?
Not necessarily. It depends on what we are looking for here. So we are looking for 8. Yeah, this we have 0, 3, 1. And then it becomes 1, 1, 3, 2. So this exits just fine. And then the second one is looking for 6. And it will get out the first time.
And then this one is one where it becomes like n is the array 4, but we don't have a 4.
Right.
And I didn't know how to trace that, like how to indicate like that's not going to go anywhere. That's not true. That's not false. That's
okay.
Does that make sense?
Okay. What I want you to realize is the algorithm should still exit, even when the value is missing from the array.
Okay.
It should still exit. Okay.
Okay.
But in this case, it is not going to.
Right. It doesn't. Yeah.
Yeah. So what you need to do is to tell me why you think the algorithm is not going to exit.
Okay.
And the reason why it's not exiting, okay, is that M?
Yeah. M is 4, and so A
But
of
why is it
4.
4?
Here's the algorithm is on the back right here. Because of the floor.
The floor?
Because B plus E.
Okay, B is
Maybe that's
2, and E is 3. So 2 plus 3 is 5. The floor of 2.5 is not
So this
4.
should be 2.
That should be 2.
Is that where I'm having an issue?
That's
Okay.
that's why you're having an issue, because if it is 4, then you'll be accessing an array out of bound.
Exactly, and I didn't know how to
That's
like write that.
not the problem.
Okay,
That is
okay.
not the
So
problem you
that's
should
where
encounter.
I'm making an issue.
Yep. So once you fix that, you will see that another problem emerges.
Is that
you
it
just have to
keeps
describe.
going forever.
Right. You just have to describe, it as, since in 2 iterations, none of the values of
have
any
changed.
variable has changed. So that's why it's going to be
Detect
an
the pattern
incomplete.
here of.
Yep.
Okay. All
Yeah.
right, that makes a lot more. I was like, I don't know how to, I don't know what to do from there.
Yeah, but that's the reason, because it's not supposed to change to 4. It's supposed to remain
As 2. Okay, so
Yep.
I just read it wrong. Thank you.
no problem.
So recursion's like a spring that you then wind, and then it solves the problem